first two problems at the interval. Yeah. So when I start to do it and try to do it, can I like show it to you after all day?
No problem. Hmm? No problem.
Okay, thank you so much.
They are easy.
They are easy?
Yeah, they are easy. They are deliberately made easy. Service to my workplace. Need more students. Nice tiny one. Small, just 700 watts. This one is photography. One view on one. Wow. We're almost. Time to get new knowledge. Time to get something new. So, yeah, something new. What I got here? I got small experiment. I have harmonic signal source generated producing 10 kilohertz of good quality harmonic signal. And two scopes. Simple. Analog scope is just for control. And this one, digital. I need to come a bit closer. Oh. Okay, we can see it. There are two nice lines, one yellow and one red. Yellow is a time space, and red is a result of discrete time Fourier transform. How to say it? Okay, it's a scope. Performs a digital signal processing, performs a discrete time Fourier transform. Shows me spectrum. What should we see? If my signal is cosine omega 0 where in my case omega 0 is double p multiplied by 10 kilohertz. What should we see?
In plus side and say conjugate of symmetrical, I mean.
Yeah. In ideal case, it's spectrum plus 10 kilohertz and minus 10 kilohertz, but because scope shows only positive, we should see something like delta of omega minus omega 0, ideal thin spectral line. Yeah, there should be ideal thin spectral line. And what do we see in the red line? Do you see? Can you see it?
It's not visible.
I don't know, maybe turn. No, it's a bad idea. This way it's worse. I see something like I don't know, maybe come closer. This red line is interesting. You see?
Yeah, it's okay. It's visible. When we
Yeah. I can change frequency a bit. Now it's more fun. See this?
Yeah, so light's playing like.
Something like this, something very strange. Yeah, it's not looking like 10 kilohertz. Very strange tailing. Yeah. Okay, you can say the scope is a garbage. Okay. Case, this scope is much better. It's real. Much better. Yeah, in linear RMS. Do we see it? yellow line signal, red line is Fourier transform. Also, not delta function. And something appears here. I can play a bit with the frequency. Whoa. What's this? You see double? 1 second, I will move it to black. What happens? Single peak with strange oscillation around it. And next moment, kind of double head in different frequency. Again, double head, single peak with kind of oscillation. Wait 1 moment. I will make things interesting. Switching to logarithmic scale. It will make small details more visible. Wait. I can get this interesting frequency exactly. Logarithmic scale reveals the details, you see, kind of strange waves. Small shift is needed to get this point. This scope is better, but I still can get same thing. You see, kind of waves. Main, peak, and kind of waves. They are very visible. This one is better, but here you can see they kind of. This one small. They are kind of smoother, but you see here something. Can I? Oh, it's a main. One more. We'll go lower. Yeah, it's remained. You can see this strange waves. Something's not right here. Why we don't see this ideal? There is a single frequency signal. It's real.
I think it's because of, distortion. Right?
We are hitting one of the basic limitations of discrete time of numerical signal processing. Let me explain. What's going on here? Whoops. Let's see. Time, my original signal. Let's say my original signal is some kind of S max cosine omega 0 time. One single frequency. Performing Fourier transform of this signal, we are expecting to see delta function in at one thin spectral line.
Yeah, like there is one component in Fourier series, others are zero because of orthogonal.
It contains only one frequency.
Yes, one.
So we should see in frequency one thin line and omega 0. Yeah? Yeah. Huh. But what's going on in reality? In reality, where the time starts for the scope? Here. And time ends here. 40 milliseconds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 400 microseconds. It's all time frame what scope C. So from the whole signal, my scope sees only time, some piece within its observation window. In theory, signal exists from minus infinity to infinity. But for scope, it starts here and ends there. Here ends the scope's memory. Here ends the signal table. So, for scope, only this part exists. All other are zeros. All other do not exist. My scope see only limited time. So real processed signal S not T is equal to original within this time frame. So if this is some kind of T0, that for time starting at T0 and ending at T0 plus observation time.
Like we're gonna use as a limitations of integral these two. Yeah?
We are looking through window and we see only part. I can, this one, red one. How can I write? I can write what my process signal is original signal multiplied with some windowing function. This windowing function equals to 0 if time is less than T0, 1 T0 time T0 plus TV, and again 0 when time is greater than T0 plus TV. Windowing function, this blue line, I can say what its magnitude is 1. So blue line is my windowing function. My scope cuts piece from the whole signal into Fourier transform goes not original as 0, but in limited time space in reality. I don't have scope with infinite memory. Anyway, processing of infinity sample stable will take infinite time. We perform a Fourier transform on my signal multiplied with this window function. What we will see? We will see convolution. Laplace transform of multiplication equals to convolution. The same. If I have convolution between 1 and it's the same as integrate from 0 to time 1 from minus tau then tau. Operation of convolution. So Fourier transform on multiplication will produce I can derive it from, it's defined in Laplace transform, but I always can substitute complex frequency with simple. So, will be convolution of original signal frequency representation and frequency representation of my observation window. Because my original signal is single frequency, I can write delta function at omega 0 with convolution of my observation window frequency transform means what I will get what? What do we know about delta function? Multiplying with delta function is like taking a sample, yeah? So it will be my windowing function offset to omega 0. For windowing function like this it's something like sine x divided by x. And we see something in ideal case we should see delta omega 0. In reality, we will get this thing is its weight will be 4p divided by TV. We can check width increase of TV. If TV goes up, okay, to infinity of white line, so S should be delta function omega 0. Let's check if I compress see how it narrows. See what happens. I increased observation window relatively to my signal frequency, and central lobe, it is called central lobe, so really narrows. But still, one frequency can be like this. It's a good version. And can be something like this. And in worst case, you can see, still doubles.
So if we, for example, instead of increasing, if we shrink observation window,
The shorter observation window,
it can
the wider will be the central lobe. And I can still see, in one case, disappear. In one case, I see nice, see, this kind of peak, and here this waves appears, but this scope can suppress them. In other case, small shift in frequency. And everything what's the meaning of this wide shoulders? I can see small signal. Small signal in near frequency will disappear. We can see what shortening of observation window, how to say it, downgrades quality of Fourier transform, makes the central lobe wider. You missed first class. say? What can we say? What can we say? Okay. Now, okay. Let's say I have my signal inside observation window, and I do have points. Points. I have measurements. These are samples inside memory of my device. 1, 2, 3, 4, block. This one is number n. So I have n samples within observation window. I took n samples. So I have values n small, where n came from 1 to n capital. Here n is 1, 2, so on. Here are my values. If I perform Fourier transform, I do a discrete time Fourier transform on this Sn. I will get some, what I will get? Some readings at some frequencies. I will get something in frequency space, which theoretically it should be in step double p divided by my signal. This one, step, is double p divided by period. This will be signal reading in frequency space. I can say they will be k when k changes from 0 to n minus 1. What's a space? Again, my signal is cut off for observation window, with observation window, point. What's the distance between 2 points, 2 measurements? Distance between 2 measurements, delta t equals double p divided by discretization frequency of one divided by f. It's my space of discretization. Actually, it will be what? TV divided by n, okay? Now, in frequency, this is in time space. What we will see in frequency space? In frequency space, reading will be with the step delta omega double p divided by observation window. Here let's say omega 0. This one will be meaning double P divided by windowing time. Center wall are drawn in case we are lucky. Maybe I can explain it better. Here is my frequency scale. Omega reading 0. Hop, 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 hop. These are, how to say, peaks, width, step, delta omega, yeah? Equals to double P divided by length of observation window. It's our frequency scale, peaks. Good. If we are lucky, our omega, it was in blue, our omega 0 match one of these peaks. Omega 0 is m delta omega, where m is an integer. In such case, I will see whoop, whoop, 1 here. They will be smaller, but as now, you see, now it's the case, I have 1 peak, but there is an opportunity to what? To get between. Another case. Another case, here is my frequency scale. Here are my frequency peaks. And omega 0 is between. That's what happens. We see real points where system will draw me chart are here. And I'm getting, you see, double here. That's what I got. Actually, it should go big. It'll go something like this. And boom, 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 boom. I get the central lobe widened. That's what this means. If there would be a second frequency, can you understand about it? Nothing. It will be hidden under this giant shoulder. Here in this area I can understand nothing. This means what close, if signal contains components close to omega 0, I will miss them. They are masked under these giant shoulders. In case my omega 0, my frequency of my signal is I took the worst case when it's exactly between lines of frequency net. it's a problem. When we will speak on, for example, AM signals, this means that I cannot analyze AM signal. If there is something, come on, wake up. Okay, then ideal case, signal of frequency match one of the lines of frequency scale. Okay. Here. Signal with significant level of second harmonics.
Professor, before this, let me ask you something. If observation window is less than period, then
we will be in big. It's a big trouble.
Yeah, and it will be something looks like this kind of double peak. Yeah.
No, if observation window is shorter than a period of signal, it will be distorted. You will see spectrum of periodic like gluing together these small cutoffs. Observation window shorter than period is a disaster. Here, I have signal with second harmonic. Now it's a good case. See how bad case looks like. Maybe here. Small second harmonic. And this is bad case. Where is my second harmonic? Oh no, I can see. Here it is. Oh. Second harmonic is unobservable. No second harmonics here. Oh, nice second harmony. You see these giant shoulders can hide usable signal. This is distortion. I don't see it because of these giant shoulders. So what should I do? One solution is to increase observation window. The longer observation, the better is resolution. But long observation means delay. Oops. not always permittable. Where's the problem? Why do I get Why do I get this? It's really is how to say superposition of two things. Of real signal and observation window. We have the side lobes because we have sharp change in observation window. If I'll take not rectangular one, but some kind of smoothen, this will suppress these artifacts from the sharp change, but these sharp changes produce artifacts, causing these side lobes. To find them,
Then it means our observation window can be not square, but some
Yes.
kind of, yeah?
exactly, we can that's a disaster. We can try to put different observation window. Maybe one second, I will find good frequency. I like this one. What can we do? We can try to use smoothened ends. This will widen the central lobe, but this will suppress side lobes. For analysis, let's say we have omega 0 and some omega 1. This is a real A0. If I apply kind of windowing function, like this, this will be some kind of AV, and I can introduce if that is actually it's reduction factor. It will be A divided by A0. fact that if I suppress side lobes, I will not lose this small signal. I need to suppress that. To understand metrics to compare good observation window, bad observation window, I need metrics. One of the metrics is reduction rate, beta. If I have some kind of windowing function, I can get AB. It's actually it's calculated as an average inside observation window of observation window function. Generally, it's a DC component of observation window. In case of rectangular window, it's one unit. So beta is for particular window. It's DC component relative to rectangular. Or in reality, it will be. Oh. In reality, it's DC component. Usually, that is nominated in decibels. So in tables, it will be 20 decimal logarithms of this. Usually its notation is decibels. Since we don't have a continuous object but measurement table, beta can be written as 20 decimal logarithms of 1 divided by n, sum where I changes from 1 to n, v values. Okay, basic metrics of windowing function. They are basic metrics. Usually, it's analyzed in chart like this, analyzing normed characteristic in space of normed frequency. Kind 0, 1, 2, 3, minus 1, minus 2, minus 3. Your windowing function will appear like this. Level minus 3 decibel. At this level, this measurement 0.5, which to analyze accuracy, width of central lobe at level minus 3 decibel is assumed. Chart itself is drawn dividing by but this chart is normalized by division of beta. This is done to make all windows chart starting from 0. At a frequency 0, they all will have separation of 0 in normalized space. Normalized frequency to make all characteristics in same frequency scale. Normalized frequency is used. It's omega TV divided by double P. This means what chart is independent of the window width. It only represents window, how to say, nature by itself. So this spacing at the bottom is delta F 0. It will be the same. It will be in same scale. And very important characteristic. This line, it's called gamma max. It's a level, max level of side lobes. This characterizes what? Sensitivity to small signals. Any signal below red line will be missed. Any signal component. So, if you have, like I do, basic harmonic smaller signal, if smaller signal is below red line, you know anything, you don't know anything about it. So this one is a resolution, precision in frequency determination. And red line is sensitivity to small signal. Also, one parameter is used. For classic rectangular window, delta F0, width of central lobe, ability to observe signal near central frequency. For a rectangular window, it's 2. There is a so-called K parameter, width factor of central lobe. It's delta F0 divided by half. If you have this parameter less or equal to 3, it classifies as a high definition window. If above 3, low definition window limits your ability to determine frequency. Okay. Let's see. Let's push mass. Set FFT window to rectangular. Now it's written I'm rectangular. Hemming. What means hemming? I pushed hemming and my window function, okay, it will be n, it's a number of measurements, will be 0.54 minus 0.446 multiplied by cosine of double Pn divided by minus 1. This function now performed by scope. And what I will get K2. It's a window of high definition and frequency. You see this peak? It's like triangle, like an arrow looking. This window offers me a good definition of frequency determination. But what about metrics? Where are my metrics? Metrics. Hemming. Where are you? No. Oh, here it is. So, for Hemming, I will get delta F0 for central lobe twice compared to ring handle. Delta F05 at a level of minus 3 decibel will be 133. K will be 2. Beta minus 537 decibels is not so important. What's important? Gamma max will be minus 42 decibels. For rectangular window, this parameter is only minus 15. Rectangular is only minus 15 decibel. It's a significant change. You see where the line is? And let me change frequency. You see what happened? No side shoulders. Implementation of Hemming window suppressed this terrible side shoulders. It's a difference between 13 and 42 decibels. I may return. Here is a rectangular window. You see level of side shoulders. Where is my signal? Signal, where are you? I don't see it. Yeah? Apply Hemming window. And side shoulders are suppressed. It's not so good in central point. I cannot determine frequency with such precision, but it's well suppressed side shoulders. Now this neighboring signal is visible. Can I have more? Blackman, Harris. Blackman, Harris. What's this? Wait one moment. Not Blackman Netto. Hayes. Blackman Harris. It's a window of quite low definition. It has quite wide central lobe. Mass for Blackman Harris is A0 minus A1 cosine double Pn divided by minus 1 plus A2 cosine of 4pn divided by minus 1 minus A3 cosine 6pn divided by n minus 1. It's a row. Inside this window is a row, and factors for this row are A0 will be 0, 3, 5, 8, 7, 5. A1 will be 0, 4, 8, 8, 2, 9. A2 0, 1, 4, 1, 2, 8. They are running. And A3 will be 0, 0, 11, 6, 8. And so what Blackman-Harris offers us at this moment appears something quite complex. Its delta F0 is A. Not so very good frequency resolution. It at level 0.5, sorry, it's at level minus 3 decibel. 197, its K is 4, its beta is minus 891, but its gamma max is minus 92 decibel. This thing is very well. It's a very good window when you need to search small signal. You're looking for outer space signals. This scope is unable to use it fully, but this line, if a very good noise resistant environment, this line will drop to minus 92 decibel. It's very good for researching of small signals. Hennig, but Blackman-Harris has a wide central lobe. It's problem. Blackman-Harris, he's Hennig. Mr. Hennig, what can we say about Mr. Hennig? For Mr. Hennig, window function is simple. 1/2 minus 1/2 cosine double Pn divided by n minus 1. Here we will get delta F at level 0.5, 1.5, K2. It's good to determine frequency, but its gamma max is only minus 31.5 decibel. So it's good to determine frequency. See, it works on shoulder suppression, but this window isn't best choice if you need to investigate small signals. It's not very best. Actually, if you're looking for very small signal, you will need to go and find container with Blackman knot. Sorry. A Blackman knot window, it has quite wide central space, but its gamma max is minus 99.8 decibel. It's a very good window for observation of small signals. It has the same mass as Blackman-Harris, but rho factors are different. 0, 3, 6, 3, 5, 8, 1, 9. It's a precise thing. It's 0, 48, 1, 7, 7, 5, 8, 2 equals to 0, 1, 3, 6, 5, 9, 9, 5, and A3 will be 0, 0, 106, 4, 1. This observation window is what you need when you try to investigate small signals. And maybe this one can offer us something different. Mass. Blackman, Henning. Oh, it has flat top. Flat top. Flat top. And this one don't have flat top. Flat top, can it help us? There is one window named flat top. It offers delta F0 10, delta F 05 386, so nothing precise about frequency. K5, but gamma max for it will be minus 69 decibels. Maybe we will be able to see it. Disconnect generator produces nothing. One second. I need to make it visible. One moment. I'll get my second camera working. And I will try to show a result. It's good scope for demonstration of bad scope. This is a rectangular window. You see for hairs, my second signal, my second harmonic is invisible. Blackman. Oh, here is my second harmonic. Han. Oh, side shoulder suppressed, my second harmonic. And flat top, side shoulder suppressed, here is my second harmonic visible. Mass for flat top. Where is my mass for flat top? Oh. Come here. Mass for flat top. Mass for flat top equals to A0 minus A1 cosine double NP n minus 1 plus A2 cosine of 4np divided by n minus 1 plus A3 minus A4 and so on. Again, is a row we saw on a Blackman-Harris. Factors are A0, 1, A1 will be 129, it's not very precise thing. A3, 0388, A4 should be 002. But what's interesting in flat top, it's very good when you need to determine magnitude of your harmonics. Flat top window appears when you need to measure. It's for measurement. Rectangular, Blackman. This scope do not have. It offers rectangular, Hemming, Blackman-Harris, and rectangular, Hemming, Blackman-Harris. So, what's conclusion? It is not possible to, pinpoint observation window for every case. You need to make some homework, you need to select the right one for your application. But without correct observation window, your processing based on Fourier transform will always suffer from low sensitivity to side lobes, and will have kind of parasite if you would like to use some kind of filter. Observation window will create these parasite orbs where not, how to say, not willed components will flow in. Yeah, problem caused by limitation. Where's the problem? Problem because you observe not complete signal, but some cut off of it. You can reduce problem by synchronizing your measurement, but this is not how to say, this solution, it's only partial solution. If you suffer from side lobes, look for right observation window. Questions? Who am I? Where am I? What am I doing here? Okay, I see no questions. I can.
Can I ask something?
Huh?
Can I ask a question?
Yeah.
Yeah, so you said you need to use the right observation window.
Yeah.
But the thing is, how do you know which one to use?
Here is the problem. You're always seeking for. You can trade precision in center of frequency for side shoulders, or you get good side shoulders. You will have wide central lobe and not well. You will be not able to determine precise frequency, or you have precise measurements of frequency, but this means high side lobes and you lose ability to measure your small signals. It's always finding a balance. It's sometimes it's try and see. You can take something like Blackman-Harris window and try to play with the factors to get optimum for your task. When it's really hard to compromise, what people do, they set a factor. Precision, side shoulders, and try, how to say, weight factors, and try multiple coefficients. It's kind of an optimization task. When we will pay for IEEE Explorer database, there are special scientific articles to how to create an optimization procedure. You actually have 4 variables. You need to change 4 variables to get best profit for you. First you determine your fitness or profit function. How to say, you set a score mark for side, let's say 6 from 10 for side lobes, 4 from 10 for precision. And then you try multiple windows on multiple sets on signal, and you will get best one for your application. It's like training an artificial intelligence. First you have a test set, and then you train your window on this test set. It's a labor-consuming task. Some people done it. The most painful, see, when you deal with simple thing like simple determine this signal or no, it's quite simple. You can try all windows. But when you seek optimal frame for your image processing, it becomes really labor-consuming work. Because whether optics, matrix, your analog to digital converter, all these plays you select. See, you not only simple select window to reflect some small signals. With this window will put a huge emphasis on your image. It's a very tricky job and labor consuming, but really it's near a random search. You search within available set of parameters until you get best balance between precision and sensitivity. Oops. Someone's still watching this. Maybe online people have questions. I'm gonna just open small insight into problem. It's selection or see you. What you need to choose? You need to choose frequency of sampling. You need no necessary amount of memory to store value stable. And remember, longer memory, longer inertia of your system. Something changed sharply, but your sliding window of processing will take all this long tail of old measurements. Shorter windows means small inertia, fast reaction. Long windows mean slow reaction. So you balancing reaction time, sampling frequency, meaning cost of your device, and right window, observation window, balancing precision and sensitivity. It's a tricky game, like designing a car. You always seek a balance between expenses. Of course everyone would like to Porsche engine or Hemi, but Hemi are expensive, so somewhere should be a balance. Hemi engine, titanium frame, nitro injection and so on. But it's not, it's too much for street car, it will miss the market. Here the same thing, you're seeking for balance. It's for when particular application on the table, you're starting maybe this, maybe this, maybe this. You seek some kind of middle balance. That's why system architects are so well paid. Okay. I see no online questions, so I can time is ending.